Hello. For those of you watching online, hello, I'm David. Hello from the past. And this is a real analysis revision seminar in semester 2, 2016. And real analysis works a little differently to the first year courses, partly because it's smaller and partly because I can't just pick something and go for it. I need to take a lot more direction from you guys who are in the room about what to do.
Yeah, could you talk about the sequences too, if you could?
So can I have a bit of guidance as to where the open and closed sets are in the course? Beginning? So I'm looking at the beginning of the course and I have some things about lower bounds, sequences,
open and closed sets for lecture 11.
which would be quite a way in. If you found them, I could look at yours. Oh, I get it. Right, yeah. Lecture 11. Are there 2 a week? So that's week 4.
So lecture 11, and there's an index at the front if you can read it.
Look at this. Almost as if you'd made it so that it was easy to find stuff in. Okay. Yeah, I totally didn't go to the level of indexes. I did have different colours for different courses of paper. I did all my statistics on pink and my pure on yellow. Chinese was blue. Okay. For those of you listening online, this is what it's going to be like, so feel free to fast forward every so often. Okay, so we've got here in lecture 10 Danny talking about countable and uncountableness, and then after that he moves on to openness and closedness. Yep. Is there a definition of open and closed here? Which I cannot find on this page. That's a theorem. So I'll just show you what I'm looking at. Thank you for letting your lecture notes be recorded. They look actually quite a bit better than mine when I was in second year. So, well done. Here it is. Okay, just needed a definition. Okay, so let's have a look. As with all pure maths, it's all about definitions, and so the definition is, this is the definition of open, a set S, which is in R, is open when for all x's that are in S there exists an epsilon greater than 0 such that an interval of radius epsilon centered on x is completely contained in the set S. That's the definition. Where a couple of sentences earlier in the notes it said that interval radius epsilon centered on x was this interval. Like that. Okay? Cool. Well, I do two things when I do real analysis. So, I mean, there's the definition, which is the source of all truth about things, and then there's a picture. And so in my head I have a picture of here's the real line, and here's my set S. Maybe something like that. And the point is that it's open if no matter where you are in this set, can you see that? Not quite. No matter where you are in the set, there's a little interval around it that's fully contained inside the set. No matter how close you get to the edge of the set. That's how I imagine it. So even if I zoom in right, with my magnifying glass on this edge here, and there's the edge of my set S. Even if I have to be really close to this edge, then I can fit a little interval around it inside the set. That's the idea of an open set. So the question is, what would cause a set not to be open? According to that picture. Yeah, no, that's not rhetorical. So there's a point that where any neighbourhood around it, that's what you mean by neighbourhood?
Yeah.
Contains a point that's not in the set. Okay. What would that look like on my picture? Right on the very end, just here. So if that point just there was actually in the set, just a second, you're telling me that if this point right here was actually in the set, then no matter what interval I picked around it, however big or small it was, it'd always have a piece that wasn't in the set. Okay. Cool. That's good. We need a picture like that. So basically, being open, you can't contain your endpoints. Cool. Do we redo open sets later in the course in contexts other than R in this course? No, it must be in topology 3. Okay. That must be in a different course. Sometimes I have trouble knowing what is in which course, especially because the economics students do a course like this in second year that's combo real analysis and third year maths, so I have trouble knowing what's where. Okay, so in my head I'm thinking that an open set would have to be made up of an overlapping or joining together separate open intervals. That's my guess as to what open sets ought to look like. Because every point in it is inside an open interval, and so it must be made by joining open intervals together. That's what my guess is. So by joining okay. That's a U there, intuition. And not being open. So just a second. Well, the opposite of this definition is there is an X where for all epsilon the interval around it isn't contained in S. So when you negate a statement with for alls and there exists in it, all the for alls become there exists. And all the there exists become for alls. And all the positive statements like is contained in becomes not contained in. So there exists an X in S such that for all epsilon greater than 0, this is not contained in S, which means there exists an X in S such that for all epsilon greater than 0, there is a point that close to X which isn't in S. Because to be in this interval but not be in S means you're within that distance of... To be in this interval means you're within epsilon of X. Yeah. Such that for there exists a Y not in S with the distance between Y and X being less than epsilon. That's an alternative way of saying it. Yes, that'll do it. Because then if there's always another Y that's not in S that's close to the X you're thinking of, you can't fit any interval completely inside S. Cool. Okay, so that's what it means to not be open. So if I wanted to prove that something wasn't open, that's what I would have to do. I would have to find at least one point in the set, generally one of the n points, such that there's like an infinite sequence of Y's that are closer and closer to X, but not inside the set, basically. So I could do it with a sequence if I wanted to. I could think about it and go, well, here's an n point of my set. Might be easier if I just use Texter. And that's my X. And I can get closer and closer and closer. So when I do this epsilon, there's a Y here. When I do this epsilon, there's a Y here. When I do this epsilon, there's a Y here. And no matter which epsilon I pick, there's always a Y that's not inside the set that's close to that X. That's what I'm thinking. There doesn't seem to be a way of turning off that air conditioning. I have to go and get my jumper after this revision seminar. Okay, cool. So we've got this intuition. What do we want to know about open sets and closed sets? We haven't got a definition of closed yet, but... Sorry? Is the empty set open? All right. Well, that's a good point, actually, regardless of whether, just the question of is the empty set open. When we did subspaces back in first year, it was a useful thing to do to go, well, here's the definition, and here's a list of things that we know must be open and must be subspaces just by looking at them without having to check all the rules. Now, we could prove them, but we could also, if we weren't called upon to prove it, just go for it and say, this is definitely a subspace. So whenever you have a new kind of object, it's good to have a list of things that are and a list of things that aren't, just so that we can get a handle on what it looks like and be able to skip some of the work when we need to. So things that are open. All right, well, the entire of R is open. Because no matter which point in R you pick, there's always an interval around it that's in R. Sweet, so we can do a proof of that if we wanted to. Proof for all x's in R. Well, for example, I1x is contained in R, because everything's contained in R. Great. Okay, the empty set is open to Proof. This is true for all the x's in the empty set because there aren't any x's in the empty set. Vacuously true. That's just the way it goes. There aren't any points for which this isn't true. So, therefore, it's true. That's what they call it, vacuously. Meaning, basically this statement, it goes back to the formal logic stuff that's in discrete maths 2, that goes, not discrete maths 2, sorry, maths for IT, that goes that an implication is true under formal logic if the premise is, even if the premise is false. Like the only time that something is false is if you've got an if-then, which is what this is essentially an if-then. If there is a point in S, then this has to happen. That's what this says. So since there aren't any points in S, doesn't matter whether it happens or not. It's still true. Yeah. Okay. Cool. Other things that are open are open intervals. Like that. Good thing they're called open intervals, because they are open. But that would require a proof to prove that it were true. Let's see if we can do it. Okay, so to be open, it says that for every x in S, which would mean that my proof would normally start with a let x be something that is in S, and then I have to show that there is an epsilon, so I have to tell the person reading it what epsilon is, and then I have to construct the interval around x of that distance and show that everything inside that interval is inside the set. So so at the end I'm going to have to say something like, therefore I epsilon x is contained in S. So S is open. It may take a bit more space than I've given myself, but I'm making a guess. So that's what it is. So you know the beginning has to be let x be in S and the end has to be the interval is contained in S. But I haven't told the reader what epsilon is, so I'm going to have to do that along the way. So I'm going to imagine this. There's A, there's B. My interval's sort of like that. I've got an x that's inside it. And I have to fit an interval around x inside this bigger interval. So it'd have to be something like this, right? That interval would fit. As long as it doesn't go all the way up to A, it'll be great. I suppose x could be at the other end, so I just need to make sure it doesn't go all the way up to B either. So I need to pick a distance that's sort of the shortest distance to the edge, and that should do the trick, I reckon. All right. That'll do it. This distance is x minus a. This distance is b minus x. I know that those numbers are both positive because x is between a and b. And as long as I pick the smallest of that, then the whole interval ought to fit inside the set. Okay. And consider that interval. So how would I tell if that interval was inside the set? Serious. How do I tell? Great. The only way to show that, well, not the only, but The fundamental way of showing that one set is inside another one is to pick something in it. So, okay, cool. Let y be in this interval. How do I show that that's inside the set? Okay. How do I show that it's between A and B? Okay. Cool. How are we going to write that down?
Okay, so because it's in that, that means that x minus epsilon is less than y.
Oh, okay. So x minus epsilon is less than y.
That's less than x plus epsilon.
Sweet.
We can also follow that. So since x itself is in AB, so we know that x is less than a, correct, and is less than a is less than x, and that's less than b as well. So we could sort of follow that through on the inequality a bit more.
So you're sort of saying since x is in S, x has to be more than A. Yep.
So then we have that. If we replace x with a there, that would give us that a minus epsilon is less than x minus epsilon. Is that
Yes, because A is less than x. So you're saying that A is less than x, and so therefore A minus epsilon is less than x minus epsilon.
yes? Okay. And then we can replace what epsilon actually is.
Okay.
So that epsilon is less than equal to x minus a.
Yeah.
So then we can also replace that with a minus x minus a.
But that would go this way, wouldn't it?
Yeah.
So we're saying that like epsilon is less than x than or equal to x minus A because it's the minimum. And so A is less than or equal to x minus. Is that what you just said?
We just use the first inequality you wrote out there. And we just replace epsilon with the top one, I guess. So we have a minus x minus a.
You might have to write it yourself in a second. I have a feeling that probably the most efficient way of dealing with this is actually to replace just the epsilon in the x minus epsilon. Because then that's going to have like a x minus a, which is just going to give me an a. I think that's probably going to be the most efficient way. So we've got the sort of epsilon is less than x minus a, so minus epsilon is greater than a minus x, which means that x minus epsilon is greater than x plus a minus x, which is a, and so y is greater than x minus epsilon, which is greater than a. Something like that. But I only came to that after you were talking about it for a bit, so I would not necessarily have thought of that first. But one of the things that you can do is try and figure out what's going to make it cancel out to get what you want. And so on a similar note, I suppose we could say that epsilon is less than b minus x, and so x plus epsilon is less than x plus b minus x, which is b. So y is less than x plus epsilon, which is less than b. So therefore y is in S, and therefore the entire interval, therefore y is in S, and the whole interval is therefore inside S because everything in it is, and therefore S is open because the whole interval's in there. Right. So already the things with open sets and a lot of these are about sets, are about that classic proof that we've got a proof structure that we can copy now that says that to show that one set is inside another, we have to show that every point in it is inside the other. And the structure we can follow is about things being close at one end and being able to replace, to try and make other bits disappear. I'm not sure if that's clear enough, but I could possibly try and do that. Okay, sweet. All right, so there's some things that are definitely open. What about some things that are definitely not open? Do you know any things off the top of your head that definitely aren't open? Yeah, I would say a closed interval. Would it matter that it's closed at both ends? Like, would it still be not open if it was only closed at one end? Yeah. Something like that. Oh, back here, what if my open interval was like this? What if it was a to infinity? Would that still be open? Yes? Why is that?
Because you can still take any point from
Yeah. So I'm just checking, rephrasing that. I didn't actually hear all the words. You could basically do this proof but only do half of it, right? We wouldn't have to do this bit. We'd only have to do that bit.
epsilon equals the minimum of x take a or b take x, b is equal to infinity, so x1 just be x take a.
Yeah. So I'll just repeat that for the recording. If b was infinity, we wouldn't even need to do the minimum. We'd just do epsilon being x take a. Because we just have to only care about how close we are to the bottom end. Okay, so we could modify that. I might even add that. Something like that. They'll be open as well. So my half-open ones, possibly things like this. Something like that. They'll be not open as well. It's probably worth being able to prove that things aren't open, and it might not be the worst thing for me to just do a proof of one of them. So let's prove that that isn't open. So how would I go about proving that that set isn't open? Where am I going to start? Sorry? Pick the point B. Yep. Consider B. Right.
And then you show that for all epsilon greater than 0 contains a point that's not.
Yep, so for all epsilon, so that means I need to say let epsilon be greater than 0. Cool. And then you want to show that there's a point within epsilon of B that's not in that set.
Yeah, but yes, consider B plus epsilon, for example.
Like that? Okay. consider b plus epsilon. So that point's not in S, because it's more than b. B plus epsilon is not in S, since b plus epsilon is greater than b. Cool. And it has to be within epsilon of b, which it is. Sweet. Okay. And the distance between b plus epsilon and b is epsilon. Oh, maybe we should do epsilon 2 then, because we want it to be strictly within epsilon. We should really just give this point a name. Let's call it y. Y is not in S since epsilon 2 is greater than b, and the distance between y and b is b plus epsilon 2 minus b, which is epsilon 2, which is strictly less than epsilon. Because when we went back to our thing there, it had to be less than epsilon for it to for this argument to work. So I mean, I think it would carry more force if we actually strictly said, therefore, the interval of radius epsilon around B isn't fully contained in S. I know that it's not necessary, but it would make this connection to the original definition stronger. So we can say, so is not fully contained in S. Yep. Okay, cool. Good. I'm really hoping, I'm just going to stop here for a second. I'm really hoping that this is useful to at least one person in the room. Is it useful to you, Charlotte?
I don't even know what you're talking about.
Ah, curses. Any of you guys? Good. At least some people are nodding. Can anyone articulate what's useful about it? Just for my own future reference. What was that? Answer questions in the exam that are about this. Okay. Do you think it'll help for any other questions that aren't about this? Possibly not. Possibly. Not sure. We'll know when we get there. Okay. So, right. So we've got openness. Okay. And we've got a list of things that are open and a list of things that aren't open. I guess the next strategy would, the next thing to know would be what things can you do to open sets? So, you know, how can you make new open sets from old open sets? We only sort of did that once with subspaces in Maths 1A or B, and you proved that when you intersect two subspaces, it's still a subspace. And you did it with convex sets in Maths 1A. The intersection of two convex sets is still convex. And that was important to linear optimization. So it seems like the things that we can do to set, which are union them and intersect them, and possibly without them as well, you know, exclude them, those are things you can do to sets, and it would be nice to know whether they preserve this property of sets. Okay. Okay, things we could do to sets and whether it preserves openness. So let's see. If S1 and S2 are open, then that definitely implies that S1 intersection S2 is also open. That's good. If S1 and S2 are open, then that implies that S1 union S2 is open. Beautiful. Those are both provable, and I will do one of them. I'll do the intersection one. It would be nice to know if we could do more than one set, if we could do more than two of them. If you had like 4 of them and you intersect them, would it still be open? If you had 20 of them and you intersect them, would it still be open? If you had infinity of them and you intersect them, would it still be open? They're good questions. So the finite numbers we can do, because the first 2 make a new open set and then you intersect that with the next one, and according to the first rule it's still open. And so you could do that with induction if you wanted to. You could prove that any finite number. But it's not true that an infinite number of intersections produce a new open set when you intersect them, though it is true for unions. So I'll put that in here. So if you've got a sequence Si for I in some sort of other set, so it could be the natural numbers, it could be the real numbers. So it always implies that the union of all of them is open. You can put any number of open sets together in any way you like. If you just glue them together, it's still open. But it doesn't necessarily imply that the intersection is open. So the intersection might not be open if the number of sets isn't finite. Okay, so there are rules for unions and intersections. So why don't we do a proof? Okay, so let's see. It's over there. If S1 and S2 are both open, we're going to prove that S1 intersection S2 is also open. Was this one of your assignment questions or something? Was it a tute? Okay. Well, I suppose same deal is the definition of openness says for all x, so let x be in S1 intersection S2, and then we have to create an interval of epsilon around x that is fully contained in S1 intersection S2. And we have to tell the person reading it, which could be future me, what epsilon is. Well, it is in S1, and S1's open, and so that rule about the open set, like the interval around x, works for S1, and it works for S2 as well. Okay, I'm going to give it a go. The picture in my head that's going on at this point is that like this is S1 here, and this is S2 here, and then S1 around my point X I can make an interval that's contained in S1, and around my point X I can make an interval that's contained in S2. And as long as I pick the smaller of those two intervals, it must be contained in both of them. That's my idea. So I'm going to say, so x is in S1, which is open. So there exists an epsilon 1 greater than 0 such that an interval of epsilon 1 around x is completely contained in S1, and also x is in S2, which is open. So there exists an epsilon 2 such that the interval of epsilon 2 around x is contained in S2. Looks like I'm going to need a little bit more space. Where's my good... Okay, so if I take the smaller of those two radii, epsilon 1 and epsilon 2, and consider x, I epsilon x is contained in or equal to I epsilon 1x, which is contained in S1. I epsilon x is contained in I epsilon 2x, which is contained in S2. So therefore, since it's contained entirely in both S1 and S2, it must be contained in their intersection. So I didn't need to specify a specific y inside that one because I could argue about the set as a whole. So that was kind of pleasant. So, and that last argument, this argument here is about just, I think we're allowed to just say it, that an interval centered on the same point but smaller radius is contained in the one with a bigger radius. I think that's obvious enough to not have to say it. But you could probably say, you know, since epsilon is less than or equal to epsilon 1 and since epsilon is less than or equal to epsilon 2, that will do it. I think that'll convince of this bit here. Okay. What about the proof that an infinite intersection isn't necessarily open? How does that go?
Sequence of intervals all centered at the same point, which the radius converges to 0 and is left with a single point, which isn't open.
Okay. So what I've had is a suggestion that you define a sequence of sets that get smaller and smaller to a single point. And so when you intersect them all, you end up with just that single point, but a single point isn't open. Oh, good. We should add that to our list before. Just a second. You're telling me that a single point by itself isn't open?
Yeah.
Single point is not open. Okay. Basically the exact same argument as just doing one end of this one, because all we needed to do this proof was the point B itself. And the argument would be, the proof would be exactly the same. This proof would be precisely the same. In fact, it's much easier because you can just say y is equal to b plus epsilon 2, which isn't b. Therefore, it's not in the set. That's an awesome proof. I like that. So if I wanted to modify this proof, I could say, consider b and let epsilon be greater than 0. Consider y is equal to b plus epsilon on 2. No, you still need to talk about intervals. That's okay. Right. But you say it's not y equals b plus epsilon on 2, which isn't b, and therefore the whole thing isn't in the set. That's great. So single point is not open, and so if I want to show, if I want to show that a sequence of infinitely many sets intersected isn't open, then I could try and do it by making a set that all intersects to give a single point. So. Okay. So let Sn be something like that. That's an interval around 0, and it's open. So if I could show that that set was just a single point, then it wouldn't be open. Well, how do I do that? I mean, 0 is in every one of those sets, and so 0 has to be in the intersection because it's in all the sets. So at least we can tell that the point 0 is in that set. So first, 0 is in minus 1 n over n for all n in n. Therefore 0 is in the intersection of all of them. That is, 0 is in the set S. Okay, so it has 0 in it. To show that 0 was the only point in it, I would have to show that no matter which other point I picked, it wasn't in all of the sets. It wasn't in the intersection. Like to show that a set is a single point, you have to show that none of the other points are in it. So I would go something along the lines of consider x not equal to 0. Because then what I can do is I can show that x isn't in this final set. Okay. Now I'm just going to draw a picture. So there's 0, there's x, and then we have these sets that are smaller and smaller, right? Like that. So this would be like S1, S2, S3, etc. Okay. So basically, as long as I go far enough, it'll clear x and x won't be in it anymore. That's what I'm thinking. So if I make my n big enough so that 1 on n is less than x. So I want, just going to do a quick calculation if that's okay. So I want 1 on n to be less than the absolute value of x. Okay, that's what I want. Cool. So choose n to be greater than 1 on the absolute value of x. Then 1 on n is less than the absolute value of x. So x is greater than 1 on n, or x is less than minus 1 on n. And so x is not in that interval. Yep. I should have done it round the other way. Just let me rewrite this. It feels better this way. Yeah. Sorry? Yeah. Yep. That's a good point. And so x can't be in that interval. Sweet. You know, it probably would have been better to just straight up do the set of like minus epsilon to epsilon for epsilon in the real numbers. That would have done it much quicker. So therefore, x can't be in S because it's the intersection of all of those. So if it's not in one of them, it can't be in the whole. Sorry. So thus, S is just 0, which is not open. Done. Okay. All right. So that's openness. So where did we go? We've got a definition of open, which is all about intervals. We know some things that are definitely open and some things that definitely aren't. We know what the set operations do to open sets, whether it preserves openness or not. That's open sets. Great. Why are open sets important anyway? Like, do they have anything to do with any of the rest of the course? Okay. Occasionally get asked to prove things about them. Mohammed, you did a nod. Where does it come up?
Sometimes in later when we look at things like differentiation or other theories, they usually involve things called
Okay. And so it only needs to be an open set and not an interval for derivatives and stuff.
Yeah.
Cool. Nice. Okay. So just a second. We are now up to closedness. So what if there are examples of closed? We say a set is closed if its complement is open. Okay. A set S in R is closed.
I think that's about all we did with closed sets. We just said that we didn't really touch on them anymore than that.
Okay. All right. However, just for completeness' sake, what are some things that are definitely closed? Just before we go back, what that means is, since the outside is open, that means it's this definition, but with a not in at this point. So to be closed, for every element that's not in S, there's an epsilon greater than 0 such that the interval around it is completely outside S. So it's not a not contained in, but it's a contained in the complement. Yeah. Okay, some things that are definitely closed. Sorry? Closed intervals. Okay. What about intervals that have an infinity in them? Can they be closed? Yes, they can. That's a closed interval because everything except that is an open interval. Everything except this, R without A infinity, is minus infinity A, which is open. And so therefore a closed interval, an interval that's closed at one end and infinity at the other end, is in fact closed. It's important. Anything else that you know that is definitely closed? Sorry? the entire set of real numbers is closed because the complement of that is the empty set and the empty set's open. And the empty set is closed because the complement of that is the real numbers and the real numbers are open. Okay. So what about anything else you know that's definitely closed? Yeah?
Could you go back to, so you have A is closed and you have infinity that is not closed. Could you talk about that? Why is it closed? But that specific thing that closed means they're open.
This is definitely closed. The definition of closed says that if you take everything except this, like the complement of it, and you look at that, and the new thing you've made is open, then the original thing is closed. So when I draw this picture, if I go A to infinity, which is all of that, everything except that is this bit, and that bit is open because it doesn't have an endpoint. We said way back here, let's see if I can find it, that something that is, so that's half open. Where's my list of things that are? Okay, open intervals A infinity or minus infinity B, they are definitely fully open. And that's what I get when I do everything except one of these. I'm going to let you ponder that for a minute, but there is one more reason. You know something is closed when no matter what point you pick that's outside it, you can put an interval completely inside, completely around it, so that it's fully outside the set. So if I pick a point here, for example, there is an interval around this that is fully outside the set. And no matter how close I get, I can pick an interval that's fully outside this set. And so therefore it is a closed set. Can you describe again what's bothering?
I couldn't really think, like, I couldn't understand why is that considered closed. Just, yeah, it didn't make sense to me.
I think the other way of saying it is that, so minus infinity to infinity, the entire real numbers is closed. Okay? This is not a proof, but it's an argument why. Things are only closed because of their end points, right? So at this end, it's definitely closed at this end. Same way as this is closed at this end. But it doesn't have an other end. And so I don't have to check the other end because it isn't there. It goes on forever. I don't have to check infinite endpoints to see whether it's closed or open at that end because there is no end to check. And so I only have to check this end, and that end is closed, so the interval is closed. This interval is closed at both ends, so it's a fully closed interval. This interval is closed. This interval here is closed at this end, but open at that end, so it's neither open nor closed. So, but this interval is closed at this end, but there isn't another end to check. That's not an end, because it goes on forever. It doesn't end there. And so you don't have to check that end, because it's not there to check. So it's closed at all of the ends that it has, so it's closed. There is one other thing that we have mentioned so far that is definitely closed. A single point is closed. So, final thing that is very much worth mentioning is that it's possible to be both open and closed. It's possible to be neither open nor closed. It's possible to be one but not the other. And it's possible to be the other but not the one. So, where it's possible to make a table like this and find examples that fit in every position. Things that are both open and closed are the real numbers and the empty set. They're both open and closed. I believe they may be the only sets that are both open and closed. Things that are closed but not open, maybe a single point, for example, and a closed interval, maybe. Things that are open but not closed, an open interval. And things that are neither, something that's open, closed at one end and open at the other. So it is possible to be in all four of those, well, it's possible to find sets in all four of those categories. So I can add to this one, you know, A infinity is closed but not open, and round bracket A infinity is open but not closed. So they're our definitions of open and closed. It's not impossible for a lecturer, even though you haven't talked about closedness much, to ask you to do a proof about it in the exam because they want to see how you cope with proving something that you've only just seen. It's one of those things that people do in exams every so often, because proving things is part of the purpose of this course, learning how to do that. And so it can't hurt to think about some of the things that you've seen. All right. I suppose just for completeness' sake, the rules for openness are the same as the rule for closed, but the other way around. So if S1 and S2 are closed, then that will mean that S1 intersection S2 and S1 union S2 are closed. But if Si for I in any collection is closed, then that means that all the intersections are, any intersection is closed, but unions are not necessarily closed. Which is the opposite of what open sets do. Open sets, unions are definitely open no matter what, and intersections are only open if I isn't finite. And it's the other way round for closed sets. Proving that the union of a union of infinitely many closed sets isn't necessarily closed is, I think, probably harder than proving that the intersection of infinitely many open sets is not necessarily open. Can't think of it right now. Oh yes. Yeah, you could do this set. Sn is like that, for example. That's a closed set, but when you union them all together, you'll get all the way up to, but not including 0. And so you'll end up, when you union them all, getting the interval from 0 to infinity, which is open. Yay. And not closed. Right. Is there any other information about open and closed sets that we've seen elsewhere in the course at all? You sure?
We do some stuff on series.
Yep. And how does open and closedness affect series?
I'm not sure, but I'm sure we
Okay. Oh, you're asking, can we do some stuff on series? Yeah.
End of lecture 27.
Just a second. No, here we go. There is one more piece of information that's worth mentioning about open and close. I'm just trying to put it all together. This is how I would normally study these things. I'd go, let's find all a reference to that concept all the way through the notes and put them together. So this one, it says here that theorem set S is closed if and only if all convergent sequences Sn with Sn inside S converge to a point in S. So that is, i.e., if Sn is a number that is in S. So basically, if you can find a sequence of numbers that's all of the things in the sequence are inside S, but when you do the limit you fall outside the set, then it's not closed. And I have a feeling that might come back, because that means that in a closed interval, if you make a sequence of points entirely inside that interval, then its limit has to be inside the interval. And sequences are related to continuity, and so I reckon that's going to be a thing. All right, just worth mentioning now. All right. Yeah, okay, cool. Moving on. So you just asked to talk about series. Tell me what week we did series, eh? Sorry? Week 10. Week 8. Surprise quiz! That's what it says in week 10. Sorry. Okay. So we have here week 10 Taylor polynomials, Lagrange remainder theorem, series. Okay. Anything in particular that's feeling dodgy about series? How do you prove the root test? Okay. I will write that down. If I forget, ask again. So series is, okay. Your lecture starts at 1, but I guess it can start wherever you like. Okay. And the definition of converging . So Sn equals the sum from 1 to n of an. This converges when that converges. Okay, so basically if you want to know if an infinite sum converges, then you add it up to the first one, and then the first two, and then the first three, and then the first four, and that makes a new sequence of numbers, and now we can talk about convergence in terms of sequences instead of series. Okay, cool. So that's the formal definition of converging. Okay. And there are some, and then like the next several lectures is all about different tests to tell whether things converge or not. Is that what the rest of it's basically about? Did your lecturer produce some sort of fancy handout with all of them on it? No? Yes? Sorry? Digital? That's fine to me. Oh, and then there's power series, which gets back to Taylor again. Oh, look at that. Nth term test. Comparison. No, this is adding and multiplying. Comparison, limit comparison, integral, ratio, root, absolute convergence, alternating series test. Nice. This seems like a useful thing to print out and stick somewhere where you're going to see it. Okay. So some of these we saw in Maths 1B, back in the distant dark ages of however long ago you did Maths 1B. So there's all these tests for telling whether things converge or not. And there's a couple that you just know converge and don't converge, like the harmonic series doesn't converge. All right. So I have a feeling that this list list given by your lecturer. I have a feeling that this list is probably is probably in a decent order for the order you should think about them. Right? Because in order they're sort of easier, the easier ones are earlier. So the ones that are easier to think about are earlier, and therefore they're the easier ones for you to know whether things really converge using them. So if you wanted to know if you just had a random series and it says, does it converge, run through this list in your head. But I have a feeling there's also some clues that will tell you that a certain test is more useful than another. So what have we got here? We've got the nth term. So if you look at the nth term, and just as a sequence of its own, if the nth term doesn't go to 0, then it doesn't converge. I mean, that's a much more useful interpretation of this test than anything else. So I would go There's a much more useful way of saying it. I mean, the lemma or whatever it is on the sheet says that if it does converge, then the limit has to go to 0. But that's saying that if the limit doesn't go to 0, then it doesn't converge. So if it doesn't have a limit at all, then it won't converge either. So the limit has to exist, and the limit, if it exists, has to be 0. If the limit is anything other than 0, even if it's like 0.00001, if it's not 0, it won't converge. And that's the first thing you should always look at. And the next thing is to try and compare it to things that you do know converge and don't converge. And there are several ways of comparing. The first way of comparing is to see, man, works better than putting it on my top. Well, that's bizarre. We have a reflection of the keyboard in the screen. So if it does converge, then, other way around. If it can be made of two other series themselves which converge, then you can be sure that it does. It may be possible to combine two series which separately don't converge to produce a new one which does. That's okay. But if you can build it out of other series, then you can do it. It's saying here that they might multiply together and that might not produce it. Yeah. Okay. So the next test is basically to build it out of other series. It's not really a test. So basically build from things you know. As long as they both converge. And so if you happen to notice that that when you maybe separate the fractions out, you get 1 over n squared and 1 over n cubed, and you go, yay, it converges, because they both converge. What's the next thing? If AN is a series with non-negative terms, then that converges if and only if it's bounded. Well, that's cool. Oh, the partial sums are bounded. Okay, not the individual terms. Right. So basically, bounded partial sums, well, bounded positive partial sums, basically. So we get basically the set of has AN greater than or equal to 0, then the partial sums being a bounded set implies that we converge. Whoops, sorry. So I imagine that if the individual terms, some of them are positive and some of them are negative, then that doesn't necessarily tell you, and if the partial sums are bounded, but the individual terms, some of them are positive and some of them negative, it doesn't tell you anything about whether it converges or not, unfortunately. Yeah, that would make sense, because minus 1 to the n is completely bounded. It only has minus 1 and 1, but it doesn't converge. But the partial sums of that are 0 and 1, and they don't converge, but it still doesn't converge. Okay. So this is the comparison one. So if your series is less than another series that converges, then that converges too. Right? So the rest of them are sort of on there, aren't they? And the tricky ones are the ratio test and the other tests that are the root tests that are further on, because they're about really quite complicated things. So what are these three? These three are about comparing, right? You can compare your series terms to another series. You can do a limit of one term divided by another. Nice. And if you treat your function of your an as a function of a continuous variable, then you can do an integral. Well, they're really clever. That's really clever. Huh. So that would be a reason why the harmonic series doesn't converge. That's so clever. Wow, okay. All right. I might as well put them in, because someone else might look at this and not have access to this thing first. So it's a comparison test. If an and bn are both greater than or equal to 0, and an is less than or equal to bn, then the big one converging implies that the little one converges. It also works the other way. If the little one doesn't converge, then that means the big one can't converge either. Cool. So if you know, for example, that's kind of cool, I like this. So, for example, you know that that one can't converge. Because 1 on root n is more than 1 on n for all n, and this one doesn't converge. So it works both ways. All right? And then there's like this limit comparison test. So this comparison test is just raw looking at the sizes of them, one is bigger than another. And then the limit comparison test is about dividing them to see if one's bigger than another. So they're all sort of logical, really. Like, if one of them's bigger than the other one, then the big one tells you about the small one and vice versa. The limit comparison test is that an is greater than or equal to 0. Crap. Bn is greater than 0, and the limit of n going to infinity of an over bn is a number where L is a positive number, L is between 0 and infinity, then both converge or both diverge. How cool is that? So just a second, 1 over n and n, when you I have to think about that one. So, but if it comes to 0, then it doesn't tell you anything. Okay. And in the integral one, you compare it to an integral. Interpret an as a function of n, and then n equals 1 to infinity an converges if and only if the integral from 1 to infinity fx dx does. Sweet. Nice. Can't think of them at the moment, but I have a feeling that these are the order that you would do them in. Like, I would try them all in this order before I would try just straight comparison before I try the limit comparison, because it doesn't require as much effort to do. And I would try the limit comparison before I try the integral comparison. Yeah. I've called it the wrong name, but that's neither here nor there. And then we've got the fancy ones, right? Oh, what did that just say? Ah, the Cauchy condensation test. Well, that doesn't sound like fun. That's kind of interesting. But anyway. So the ratio test is from Maths 1 at B, and then the root test is interesting. All right. So I like the ratio. So basically, the ratio test is like the limit comparison test, but when you're comparing the sequence to itself rather than to a different sequence. So with this series here, limit comparison, I've got two series and I'm comparing one to the other. But with the ratio test, you're comparing your series to itself. So you're saying, you know, well, so in this ratio test, your lecturer has specifically said the ratio test only applies to series that have positive terms. And in Maths 1B, you put an absolute value on there. And that's why what you did. You made it positive in Maths 1B so that you could use this test. So calculate. So use for an greater than 0. And then step sort of 1 is calculate an plus 1 on an. So each term divided by the one before it. So an plus 1 divided by the one before it. And then you go, you find the limit of that as n goes to infinity, then and then you'll decide what happens based on what that limit is. L is less than 1 means converge. L is greater than 1 means diverge. L is equal to 1 or does not exist means, I don't know, could be anything. Back in Maths 1B, if you had a series where the ratio test gave you exactly equal to 1, it was usually an indicator that you probably should have done the very first test, which is see if the individual terms go to 0. So often the ratio test coming out to 1 is an indication that one of the earlier tests would probably have worked rather than this one. So considering the ratio test is sort of really low down the list on things that you should try, if you do it in sort of the order of things that are easiest to do, you probably won't end up in the situation where the ratio test gives you exactly 1, because you will have already decided whether it converged or not by the time you got there. So, yeah. And now we're finally up to the root test. So now we're comparing, oh wow, okay. AN is greater than or equal to 0. So we're going to, step 1, we're going to, well, I don't know. I don't know if this is a thing that we can even do. But we want to do the limit of this. Of n to the 1 on n. And it'll come out to an answer. And basically it's the same conclusion as the ratio test. L is less than 1 means it converges. L is greater than 1 means it diverges. And L equals 1 or doesn't exist will mean we don't know. And your question, Adam, was how do we prove the root test? But I suppose before we do that, I'm just going to tack on the last few on the list. So the last few on the list was compared to its absolute value version, which is basically what we've been doing for all of these. And in fact, that sort of is one of the first things you should do. Like right up the top of the list. And in fact, I'm wondering if there's space to squeeze it in or not. Probably not. But right at the top of the list, you should just go if it has a -1, like if it's, do the absolute value and look at that instead. Because if it converges, if its absolute value converges, then it will converge too. So I'm going to just have to put a note here. So this isn't really an absolute value thing, but this isn't what it's called in your notes, but I'm going to call it that. Compare it to the absolute value. And the theorem goes, or the lemma says that if n equals 1 to infinity, absolute value of an converges, then n equals 1 to infinity, an converges too. So if ignoring the fact that it flips between plus and minus 1, you can tell it converges just from that information, then that's enough. So basically that means that you should probably try this early and go, oh, it's got a minus in it, sweet, I'm just going to check. And I'm just going to pretend that it doesn't and do that instead. So sort of in a way, these last two are about series that aren't always positive. Because then there's the alternating series tests. Oh, remember this one works backwards, but in the negative, right? So if a term that has negatives in it doesn't converge, then the positive version can't converge either. But that works when it's backwards, everything's not. So the alternating series test is the last one. is that if an is like minus 1 to the n or n plus 1, it doesn't really matter, of some other term where they're all positive, right? And these terms are strictly greater than zero, each greater than each other. Like the first one is the biggest. And they're all greater than or equal to 0. And the limit as n goes to infinity of Bn is 0, then that means it converges. So that's 3 bits of information in the alternating series test. I tend to call them number 1, 0, 1, and 2. The reason I call the first one 0 is because that's telling you it's an alternating series, so it doesn't really count, because it's the alternating series test. It only applies to alternating series. So, so if you do see something that flips between plus and minus 1, the first thing you should do is either, these are the 2 things you can do. You either look at the alternating series test and go, strictly decreasing sequence, bam, done. Or you look at it without the minuses and see if any of the other tests apply. And basically what that means with this absolute value is that any of the previous tests which say they only apply to a positive AN can now be applied to anything that's like absolute value of whatever is there. And you can do it that way instead. Which is why in first year the ratio test was done with an absolute value. Because you're basically doing absolute convergence and then doing the ratio test. So, I have an important question. Do you think it is something that is important to know how to prove that any of these tests work? Is that something that happened in the lectures, that the lecturer proved that they worked? No? Sorry? Did he prove the root test?
It was in one of the tutorials.
It was in one of the tutes. That's interesting. All right. What sorts of strategies did the lecturer use to prove some of these things?
Sometimes you can just use that in
Okay. Well, let's attempt to prove the root test. What time are we in? All right. If I can't do it in 10 minutes, I'm going to stop. Which seems likely, but we'll see how we go. Okay, so what we want to prove, I may only prove part of it, maybe the bit where if it's less than 1 then it converges. So suppose we have a series with AN greater than or equal to 0. That's how the root test went, wasn't it? Yep. And the limit as n goes to infinity of AN is L. Okay. So how about we attempt to show that if, well, I suppose we'll go, that's what we need to do, isn't it? Yep. So we need to prove that it converges. So either we turn this into something that we can use one of the other tests for, like I can use an earlier test in the list, or we go straight to the definition of what it means to converge. Well, since it's a proof, I'm going to sort of run with what it means to converge. I think I might possibly have it, actually. Let's see if I can do this. So let Sn be the sum from n equals 1 to nan. So converging will mean that Sn is a sequence that converges. That's the same as the series converging is the same as the sequence of SNs converging. And we just had a thing before that says that if the sequence of partial sums is bounded, then it must converge. Bounded partial sums. So we've got an is greater than or equal to 0. We've got Sn. If we can show that Sn is bounded, then it'll converge. Okay, that might do the trick. Not sure yet. I'm just trying it out. So I suppose technically we... All right. That's what that is. So if n is like, this is my feeling about this. If n is far enough out, then we know that the nth root of an is approximately L, nearly. But this is not a proof, this is just me thinking it through at the moment. If n is big enough, then an is approximately equal to, an to the 1 on n is approximately to L, so an is approximately equal to L to the n. Yep? Which means that sort of Sn, L to the n. And that means that my series is now sort of approximately a geometric series. Yeah? And so a geometric series will converge when its number that's at the bottom there is less than 1. That's my guess at what's going on here. That's my feeling about what's going on here. So, I might have to do some things with some epsilons to just be more convincing. And I suppose that if I can show that an is less than some other number to the n, and that number itself is less than 1, then I can use my I can use my ordinary comparison test to do the trick. So that's my idea. So I can sort of, without loss of generality, because if the beginning of the series doesn't apply to this approximately equal to the L to the n, it doesn't really matter, because it's only the end of the series that matters, the infinite part. Because the beginning is finite and I can just adjust that however I want. So as long as I don't adjust infinitely many terms, I'll be okay. So that's my instinct for what's going on there. So if I was asked to prove such a thing like this all up, my first instinct would be to say, well, it's approximately equal to L to the n, which makes it approximately a geometric series, and that means that the L should be less than 1 to converge and greater than 1 to diverge, and that's the reason why. If I wasn't asked to prove it, but just asked to explain why, that's what I would do. I would do an explanation which says that it makes it approximately a geometric series. To prove would be a different story. So this limit going to L means that no matter what epsilon I picked, there would be an n such that, like a capital, well, I might use m, such that when little m was more than that, it was within epsilon of this L. So that's my thinking. So there exists an m in n such that A is this. There exists an m in. I'm not using the n because I've already used capital N, such that is less than epsilon, i.e. an to the n is between epsilon plus L plus epsilon and L minus epsilon. And so, so if we fix any epsilon in particular, we've got a number L plus epsilon there that it's less than. Yeah, that'll do it. Yeah. So if I did, I'm just going to go suppose L is less than 1, right? And choose epsilon so that L plus epsilon is still less than 1, which we can do if L is strictly less than 1. We just choose epsilon to be half the distance between L and 1, and that will do the trick. And sort of denote like K. And so then we're going to have then an to the 1 on n is less than k for n greater than or equal to m. And then what we're going to do is we're going to say that it's a geometric series from that point forward, from m forward. And so we can, because the comparison test doesn't have to be done for every m, it just has to be done for all the m's after a specific, all the n's after a specific point. So we can say consider that one. Yep. Great. This converges since k is less than 1, because it's a geometric series, and that's a separate piece of information that we're allowed to use. But and also an to the 1 on n is less than k So an is less than k to the n. And so, for n greater than m, so by a limit, so by just the comparison test, also converge. Yes. Yes. Did it. And then I suppose we could say, suppose L is greater than 1, choose epsilon so that L minus epsilon is greater than 1, and then we can do exactly the same thing with another k, with another k, but this time it's going to compare it. We've got my thing is greater than something, and the other one doesn't converge, and so this one can't either. Then an 1 over n is greater than k for n greater than m, and an is greater than k to the n. And then we'll just do the whole thing, then it's complete. So consider n equals 1 to infinity of k to the n. Diverges since k is greater than 1, so by the comparison test an has to diverge as well, since its terms are more than the other one. I did it in 13 minutes. Okay, I did okay. That's a nice one. I could see that in an exam, because we sort of used the definition of limit from elsewhere in the course and other information that we already had to do this. Yeah, I kind of like that. Okay, well that's as much as I can do today. Yes, I will need to eat. Thank you very much for coming. At some point tomorrow this will be online and I'll email you all to let you know. Thank you.